systems, VLSI, IoT, and interconnection networks while working at Intel, Cray, SGI, and startups. He holds more than 10 US granted patents and has published more than 30 technical papers and book chapters. He has a PhD degree in the computer science from the Ohio State University. So let me welcome Donglai Dai, and he will be talking today about the deep introspection for deep learning and exploiting offloading capabilities of Bluefield adapters using the MVAPICH2 library. So Donglai, please share your screen and you can get started.
Does it come out okay?
Yeah, the outlines are coming, so you may need to go into the full presentation. Yes.
Okay. Hi, nice to be here, and thank you, Dr. Panda, for the nice introduction. Okay, today I'm going to talk about deep introspection for deep learning and exploiting offloading capabilities of Bluefield adapters, and this is built on top of MVAPICH2. Okay. So this is outline, and I'll give a brief introduction, especially about our company. And I'll touch on two main products from us. One is called Xscale AI, which is for a solution for AI problems, HPC systems. And the other one is Xscale HPC itself. And this is providing MPI solutions for HPC problems. Then I'll conclude. And about us, and we as a company bring innovative and efficient end-to-end solutions of services, support, and training to our customers. We leverage the full potential of a customer's cluster system for our customers' users as well as their applications. And we provide commercial support as well as training for state-of-the-art communication libraries, specifically including high-performance and scalable MVAPICH2 libraries and its families, including MVAPICH2X and GDR, Azure, AWS, and OSU INAC. The other one also include is high-performance big data libraries, including RDMA for on top of Hadoop, Spark, HBase, as well as Memcached. And in addition to that, and we provide commercial products and services. And here are the two products currently we are providing to the general public customers. And one is the XAI, the other one is Xscale HPC, which I will spend most of the time to talk about. And we are a silver independent software vendor member of the Open Power Consortium, and we're a winner of multiple DOE SPUR grants. We provide commercial support for MVAPICH2 and high BD and high DL libraries to US federal national labs as well as international supercomputer centers. We right now we have two integrated, highly integrated product to support HPC cluster systems, which were first introduced in last year's Open Power Summit. And as I mentioned before, those are the two products. And today, I'm focused on the two product itself. So now let's get on to the first one. And this product is the target for this is provide high performance solution for distributed training of complex AI problems, specifically targeted for modern HPC platforms. The main feature include And this is built on, all this one are built on top of MVAPICH2.
We are not hearing you. Is that correct?
Yes, Dr. Barna.
Yeah, okay.
What happened?
No, I think you were muted or something. So
Now it's coming back?
yes, now it is coming
Okay.
back. Yes.
Where did I drop out?
Almost in the beginning. So beginning of this slide. Yeah.
Oh, okay.
Yeah.
Okay.
No. Yeah. So.
Okay. So this product itself is targeted for high performance solutions for distributed training for complex AI problems. The main feature include the MVAPICH libraries, and we fine tune and provide great performance as well as scalability enabled by the MVAPICH2 libraries. And it's also included, this is integrated packaging to run various deep learning frameworks, including all the popular ones like TensorFlow, PyTorch, MXNet, and others. And we're specifically targeted for both CPU-based as well as GPU-based deep learning training. And recently, we have developed new capabilities, and those include integrated profiling as well as introspection support for deep learning applications across software stacks. And it provides cross-stack performance analysis in visual manner and help users to optimize their DL applications and harness higher performance as well as scalability. I will give more details on this. And we enable out-of-box optimal solution performance. And I'll give some simple demo on this, as well as one-click deployment and execution. And this tool supports both x86 and open power platforms. It supports the InfiniBand, Rocky, and NVLink interconnects. Those are the modern interconnects used in high-performance systems. Okay, here is what the DeepIntrospect tool can be used to solve the user's problem. And as end user, let's see in the middle, and showing here, it brings its own application use, deep learning model, as well as pick its own popular DL framework, either TensorFlow or PyTorch or something else. Most of that is supported by our tools. Then use this DeepIntrospect tool will help to do profiling, monitoring performance, and help analysis during training phases. And here is an overview of the software architecture of the DI tool. And at the top, you can see that it's various applications, frameworks, including TensorFlow, as well as PyTorch and Horovod. And at the bottom, it's a hardware as well as the drivers hardware solutions. Okay, and the low level machine level libraries. And in the middle, it's where we put this Introspect, which will do the performance monitoring and do profiling, as well as logging some important events and doing the logging parsing. And all this kind of information we believe is necessary for understanding the performance and the interactions between those different components from the software software stacks. And all these informations are stored in the data store. And to help us to analyze what's going on, we also provide a visualization tool to understand this. And there is a connector between the back end, which has the data store, and the front end to visualize it. And so this is what the next few slides, so I will demonstrate how easy it is for us to install and use the tools. So when you get at the beginning to install it, basically you type in provided information for the CUDNN library as well as a CUDA home path in your own environment. Then you just type one command, simple, for installation. And then the installation process will start. And it goes through the whole process, install different components in the software stack. And in the end, it will tell you whether it's successful or not. Okay, so that's the whole process if you go to the end. And then the next one is I show you a simple way to run this. So this is the command you use to run with this our software stack, as well as the whole the DI tools inside. And it's the command looks like something similar to MPI run, but this will this command launcher, this job launcher, will enable not only the software stack, the whole software stack, but also the DI tools we provided inside. Okay. Then the normal application information will show once you start running. Okay, now we see how this tool can be simply installed and start running using it to run. And so all these are of the DeepIntrospect are available in the our product Xscale AI version 1.0 package, which will be released shortly. And as an example, after you run, this is an example of output in text format. I'll soon cover the visualization part, okay? And as you can see, we collect all kinds of stats associated with communication specifically. And if you're looking at the left side, this top section is the total number of calls for different collectives, okay? And actually, even here, we can see, sorry. Even here, we can see that we actually bring this down from the application calling, the MPI or nickel, if it's enabled, or this another part is the Harvard, which means the Harvard internal orchestration calling using the MPI to do that. And the next section is about the total time spent on these calls. And yet another section at the bottom shows the breakdown distribution along different message sizes. And we do this text is normally easier for human to read and for machine to exchange information. We also have stored similar information in JSON format. And this is the visualization part. And because the text is easier to understand, but hard to detect the trend or quickly find the potential problems. And here, as you can see, this is just part of the visualization part. The whole thing can be much longer than this. Okay, and at the top, it's either how many processes you use to run this, and how many nodes you actually used, and this is command line, and the rest is showing the breakdowns for different statistics about specific communication operations. And here I only show one important one actually for DL, especially for Harvard, this kind of thing, is the MPI all reduced. Okay, and you can see we show here is how many total calls and the total time, as well as tax. Tax basically is a breakdown of different categories as shown above. And here it has a curve to show the latency and total cost and their distribution along different message sizes. And here is a detailed count on that. And for latency, we have average, we have mean and max. We're breaking that down. And so this is just one, showing one collective operations. And we have this, like what we showed previously in the text, all kinds of different stats on different operations. Okay, now this one, at this point, you may have a question says, okay, how do I use these tools to solve my problem from the DL perspective, application perspective? I'll use one concrete example to show how this helps us to actually doing the performance analysis and identify bottleneck. And this particular example is the Deep Lab version 3, okay. And this application uses large models and with many parameters. And if you look at the curve here, and this is a total distribution, total communication time distribution along different message sizes. As you can see that normally this looks okay, but there is a sudden peak at the end. By the way, that is about 64 megabytes message size. And also there's quite activity, many different number of operations are occurring at this part. And based on these statistics, also based on our understanding of the framework, we noticed that the Harvard used, we have the Harvard Fusion enabled. So Harvard Fusion has a default buffer size of 64, and that's potentially caused this, and suddenly it's all waiting at that point and happen. And another one is the cycle time of 3.5 milliseconds. Okay. And this shows suddenly occurring here, and it's suspicious for that. Both of these seems to cause maybe a bottleneck for the performance. Based on this analysis, and we do some adjustment to the parameters, do the tuning, and we can enlarge, double the buffer size as well as increase the cycle time for that, for inside the Harvard parameter tuning. Okay. And as a result, as you can see that these orange ones, the blue ones is what orange is. The orange ones is showing much more smooth distribution and total execution time for each of the operations at the different sizes. Okay, now all this seems to be good, but at the end, what does the application get? And here is what from the application overall execution time. And as you can see, for different number of GPUs, and this showing clearly at the higher number of GPU you use, basically you will have larger clusters to run the application. And at the low end, it doesn't show much because not much of a communication is needed. As the system, the parallelism increases, the benefit is showing significant. improved with this adjustment or fine tuning. So this is how this this tool can help us to understand what's going on in your application and fine tune what kind of things to improve the performance. Okay, now next I'm going to talk about the next product, the Xscale HPC. And this package is providing a scalable solution of communication middleware based on the MVAPICH2 library. It's also out-of-box, fine-tuned, optimal performance on various HPC systems, including GPUs and CPUs. And specifically, new capabilities we added is the MPI communication offloading capabilities to ARM-based smart NICs, like Mellanox Bluefield NIC. Okay, and I'll spend more time on this. So to give a high-level overview what the Bluefield is capable of, and this is the overall architecture. So I'll just highlight a few things. First, it includes a group of ARM core, and for this generation of the Bluefield, it has 16 ARM cores. Okay, and it's actually ARM core is relatively powerful in the sense it also supports neural SIMD unit and provide a coherent cache. And it including the Connex X5 interface, network interface. Okay. And has the standard RDMA as well as the VPI port and Ethernet as well as InfiniBand. In our test here, we'll show InfiniBand. Okay. And it has the PCIe connections to the host, and it has quite some more configurability associated with it, and also has some local memories used for the NIC, especially the ARM core. And the basic idea for the offloading is we believe we can take advantage of the ARM core capability to offload especially the non-blocking MPI calls. And as showing on the right, so assuming that you have multiple computing threads on the host processor, let's see, Xeon or Power. And right now, whatever we're using is on the Xeon processor. Okay. And so we are trying to find the balance and what communication task can be offloaded and to the smart NIC and still make it beneficial from the overall computation perspective. So the main idea is exploring or optimize the overlapping between computation and communication. And the solution itself is including point-to-point and collectives. And in this talk, we'll focus on the collectives first. Okay, so this is what this library including the offloading MPI calls to the ARM cores on the Bluefield adapter. And we're focusing on the non-blocking collectives. And performance is the benefit is depend on the varying number of workers per node. Workers here, we mean the ARM core. Okay. And here we use the micro benchmark, the OSU micro benchmark, to evaluate the performance benefit. And as you can see here, we show just this is measured on a cluster of 4 nodes, and we're using 16 processors on that each node. Okay, and total is 64 processes in total. And this is execution, execution time, overall execution time of that micro benchmark. This we are showing is all to all. We also have numbers for other collectives. Okay. And so we show 4 curves here, which the blue one is MVAPICH2 the base one, okay, which has no offloading. And the other 3 is 1 core enabled, 2 core enabled, or 2 workers core enabled, and 4 core enabled on the ARM core to do the offloading. And here is a distribution along the message size of that all-to-all operation. And this is the overall execution of that micro benchmark. As you can see, when the message getting larger and larger, and the benefit is showing noticeably increased. Okay. And we have take multiple tests on different configuration. This is another example of the similar test, but with a different configuration. And this is on 8 nodes with 20 processes per node. This process means computing process or application process. Okay, so total is 160. Okay, and this one will see more improvement. And one thing, if you noticed, is as we increase the number of workers on the ARM core, the benefit increases. But actually, there is a limit when you increase more and more, the benefit is increase is getting reduced. And that was because when you have more cores, the network bandwidth is reaching its limit. Okay, so enabling more cores does not show too much additional benefit. However, because of each generation, the ARM core speed, as well as the bandwidth, network bandwidth, as well as the host speed are all advanced at a different pace. So this kind of things depend on different architectures. We need to adjust all this, but this overall scheme as well as models will work. Okay. Now we see how this is showing evaluate benefit at the micro benchmark. So overall, how do we see this impact from the application perspective? Okay, we'll use one example of application to show this actually is beneficial. And this application is P3D FFT. It's a widely used parallel 3-dimensional fast Fourier transformation, okay, FFT library. It overcomes scalability problems of FFT itself, okay, by using 2-dimensional domain decomposition algorithm. It is portable across many different system platforms. So, and this is not just for some specific ones we fine-tune this. And its communication characteristics is it's dominated by frequent MPI all-to-all calls. And that's why we pick the previous one. We just show that benchmark evaluation. Okay, so here is what it's capable, this offloading is capable to improve the application for this particular one. And since this one is a 3D application, it has an input data size controlled by XYZ 3 dimensions. And to keep things simple, we only change 1 dimension and keep the other 2 fixed. And as you can see, this is showing the improvement of overall execution time. Okay, compared to without offloading. And we show here with 4 nodes as well as 8 nodes. And we show 10 smaller number of processes per node, as well as larger ones. One is 10, the other one is 20 on both of these configurations. As you can see here, when the node remains the same, the number of processes increase per node, the benefit is increasing. And if the total nodes also increases, this benefit becomes more prominent, okay, more significant. And overall, the total number of threads, computation thread, increases. That means, that normally means the communication becomes more prominent, and the impact of this offloading becomes more significant. Okay, that conclude my main talk. So we expect the exponential growth in HPC and deep learning, which requires advanced designs in middleware and tools to harness performance and scalability. We have two products specifically targeted for this. One is X-Scale AI, which provide high performance solutions for distributed training of AI applications. And DeepIntrospect tool, which we recently developed can be used to explore HPC technologies for deep learning on either x86 or open power platforms. And the other product, Xscale HPC, is providing optimized MPI libraries on various HPC systems, including GPUs as well as CPUs. Its capability to offload MPI functionalities to smart NICs, including Mellanox. Okay, just a moment. Bluefield adapters and harness the performance and scalability for MPI MPI applications. So if you are interested, please contact us for a demo and a free trial of our product. Okay, thank you for your attention and time. I'm open for any questions.
Yeah, so thanks, Donglai. There is a question on the QA box,
Okay.
whether you can read it directly or I can read it to you.
Let me read it. So, ready to learn? No.
Q&A box on the Zoom.
Oh, on the Zoom, I was thinking it's channel.
No,
okay.
no. Let me read it. Let me read it.
Okay.
It will be quicker. So it says, what type of information is provided by profiler and performance monitor components? Is that for end users or more for system or software engineers?
Wow, that's actually a very good question. Now, we actually collect relative communication, collect statistics on most of the communication costs, including point as well as collectives. But we noticed that at least right now, the Harvard or relative other framework for distributed DL, the collective is more dominant. So we only show that. But the thing is, for this collective, how it can be used, we want it to be useful for both library developer as well as system managers, okay, system administrators, but more so for end users. Okay, so this statistic is collected, as you can see, from the application, as well as for the Harvard or other similar framework for distributed DL. Does that answer the question? Hello? Can anybody hear me?
This question was put on the chat.
Yes, I can.
Okay.
Any other questions from the audience? Okay, so if not, let me thank again Donglai. So we'll move to the next session.
Okay, thank you.